models, the volume versus contact reactivity. And as you saw yesterday, these things can get ugly fast. So I'm not going to spend enormous amounts of time going through all the detail of writing down the models. That's basically what we did yesterday. But the point is, once we kind of have these various operators, and in particular, I'm not even going to write down the forward reaction operator for all the models, because for the Stochastic, or the contact reactivity pure absorption case, it gets pretty ugly, and you'd have to have delta surface measures and things. But we'll kind of get it formulated, at least in a simple case there. And then we'll see how just basically by doing operator splitting on this, we get the simulation algorithm of many Brownian dynamics approaches in simulators. Not all, but many kind of use this approach. First, there was a good question yesterday that a few people asked. Can everyone see this okay? Yeah? About this first term. And several people asked, why is there no volume here? Right? So alpha times V is the total rate that the zeroth order reaction occurs. Okay? And so the point is really the better way to think of this is that this should be alpha V times 1 over V. And that says this is the rate that a molecule gets created when you're in a state where you've thrown one away. Right? So it's the state where there's one less A. Alpha V is the rate that a new A gets produced. 1 over V is just the probability density that the new A you produce gets placed at the position of the one you threw away. Does that kind of make sense to everyone? So you need a way to actually place the molecule down. But of course, when you multiply that out, the V's cancel. So anyways, if that was bothering you, if it doesn't bother you and I confused you more, just ignore it. But if that was bothering you yesterday, I hope that helps a little bit. So, okay. So let's go to the first order reaction, A goes to B, and just write down what it is, and hopefully it will make sense to everybody. And let's see. Do I trust myself to do it off the top of my head? Probably not, but let's try it. Okay, so what is that term going to be? So now let's look at the reaction A goes to B at rate beta. So beta is just the probability per time. So an individual A molecule, right, is just going to have some exponentially distributed time that will flip into a B molecule. Okay. So what's that going to give us in the underlying equations? Well, we'll get an operator R1 A, B, C acting on F, A, B, C. So I've switched notation a little bit to what Pete suggested yesterday, since maybe subscripts make more sense here than superscripts. Okay, so what you have to think about here are there's basically going to be two terms, right? How I get into the current state and how I leave the current state. So how can I get in? Well, I have to be in a state where I have one less A and it's positioned where one of my, I have one less B and one extra A positioned where that B was, right? So I'm going to have a rate beta. I have to get rid of the B's. So I sum over all B molecules of a state where I have one more A and one less B. I add my A at the location of the B that I throw away. I get rid of that one B. And that's my incoming flux term. Hopefully I've got that right. So it just says basically those are all the possible states I can be in that bring me to the current state. And that's the rate that I'm going to transition in. And yay, I've got it right. And then how do I leave? Well, it's exactly what someone said in their question yesterday. There's A ways that I can leave because I have A different molecules. So the total rate I go out is minus beta A times F, A, B, C. Does that make sense to everybody? Does that kind of match up with your intuition? So it just says basically every molecule of species A flips at rate beta. I come in where a state where I have to have one more A at the position of the B that I threw away. Because the basic assumption we're going to make is when an A turns into a B, it doesn't move around at all. It's just wherever it currently is, it changes state. We relabel it. Okay. So if anyone actually did the exercise I mentioned yesterday, here's another one you can show. you can now show that in this model, that the probability that you're in the state, you have A molecules of species A, B of species B, and C of species C at time t. So the kind of, if you project out the spatial coordinates, should satisfy basically the standard master equation. So alpha v p of A minus 1, bt, ct, minus alpha v p of A b ct. That's from the 0th order reaction. That was what I had given you yesterday. Okay. And then now from your new reaction, you would have beta A plus 1, P of A plus 1, B minus 1 CT, minus beta A, P of A, B, CT. Okay, so basically, with what we've put in so far, our spatial model, if you look at the probability you just have a certain total number in the system, is exactly what you would get in the well-mixed model. Okay? So that's what we've got so far. And now we come to the bimolecular reaction case. So this is where things start getting interesting and a little different from the well-mixed case. And what in particular we'll see is that there's a variety of different models, like I mentioned yesterday, that we can use for the association reaction. And there's many different ways we can think about where to place things when they bind and when they unbind. And those choices will affect different properties of the system. And so I think maybe the best way to do this is to start with a simple example where we're not writing the general equations and then come back to the general equations later on. So let's start with just a simple case. The easiest case we can think of to write down how things can react, which is just have 1A, 1B, 1C, and only let the A move. Okay? And then we'll come back to this general case in a few minutes. So to illustrate our reaction, A plus B goes to C, we're going to look at a system, assume we have 1A and 1B. The A can diffuse. The B is stationary, located at a point x naught. Okay? And when A and B bind, I'll assume that C is also stationary. So I'm only going to let A move. So you can think of this as binding to a receptor or a DNA binding site. Or if we were in free space, this would be, you could think of it equivalently as the motion of A relative to B. Okay? But it's much easier to write things down in this case. So I want to kind of start with this simple example. So A can diffuse, B is stationary, and when A binds, C just sits at x naught. Okay, so that's our basic setup. And let's see. Do I want to do it? I guess we can do it in free space. I don't need a bounded domain. So let's do this in free space. So let's just assume here's my C molecule sitting at x naught. My A molecule diffuses around. And when it gets within about a binding radius, various ways it can react. Okay. Good. So let's write down the different models, because there's several different types of models we can use, and we'll see a little bit about how they're related too. So the first one I want to start with is the volume reactivity model. So if you remember in this model, the idea was that when the A molecule is within a distance RB of the target B molecule, and this of course is a typo, A binds B. When A binds, C sits at x naught, but A binds to B. When A is within RB of the target, it binds with some rate, which I'll call lambda. Okay? So our assumption is going to be that we'll let x equal the position of the A molecule. We'll let rho of xt be the probability density A is at x at time t, so it's unbound. So that gives me the equation for the probability density that A is at a given position and not bound. And then I have an equation for the probability that I'm in the bound state. So this will just be the probability that A is bound to B. Okay, so I think if you've looked at Mauricio's poster, I believe you have this model basically on your poster, a form of this. So he's basically worked this kind of form of the model as something he looked at, and many other people have looked at too. But you can read more about other ways of approximating it there. So the basic assumption then on how things are going to work that I'm going to make is the following. So we'll say that d rho dt, the A molecule just diffuses around with some diffusion constant. When it gets close enough, it can react. So we'll have a rate lambda that it can react. And then it has to be within RB of the target. So here, this is just an indicator function. I just mean that this is 1 when the separation is on the interval 0 RB. Is that clear to everybody? So, okay. So that would be our binding mechanism. My molecule diffuses, and then when it's within RB of the target, it reacts with rate lambda. So lambda is going to have units of probability per time for a reaction to occur. And then you have to have an unbinding reaction. So when the molecule of A comes off of this bound C particle, where should we put it? Well, there's a lot of different choices you make. I'm going to make one that's consistent with what's done in some of the papers by Roddick and Kostis and others, which is to put the molecule at the same position as where it unbinds. Okay? So I'm going to make the assumption that when an A molecule unbinds from a C sitting here, it just gets put there. Okay? There's many other choices you could make, but that's the simplest that I think we could take for today. So I'm going to assume that when you come off, you get placed, you come off at rate mu, and you get placed at x minus x naught, and you come off with density p rho of t, rho v of t. Okay, so we'll write out maybe in a minute what the parameters are. But here, mu is the off rate, or the unbinding rate. This is the probability density that when I unbind at x naught, I get positioned at x. And then this is just the probability that I'm bound. What about the other equation for rho? So rho b, the probability I'm bound, is just going to be the total probability per unit time that I bind, which is the integral of this. So it's just going to be the integral over the ball of radius rb about x naught of this guy, right? This thing is 0 except when I'm in a ball about x naught. So as if I integrate over that ball, I get the total probability per time that a binding event occurs. And then you just fall off, and I left out one thing there. I left out where you're going to place the molecule. So actually, that's important. Let me put that back in. So let me be a little more general. So I'll integrate over all of our, say we work in 3 dimensions. So where should I place the molecule when binding occurs? So in this case, whoops. All right, in this case, I'm just placing it at the target, so there is no issue. I was thinking about the multi-particle case where it's trickier. So here, actually, what I wrote was right. So this is going to be rho of xt dx. So that's the total flux into the bound state. And then you just fall off at rate mu. Okay. So is that clear to everybody? I know I was thinking of the multi-particle cases where there's other things that come in. But basically, you bind at rate lambda when you're close enough. When you unbind at rate mu. And when you unbind, you just place your new molecule at the same position as where the C molecule is. So more generally, you could replace this with the density m of x that would give you, say, the probability density that when you unbind, you place your molecule at x. And you could make many choices for that beyond just putting it at the same point. And we'll see actually another choice in a minute when we talk about the contact reactivity model. Okay, so if that's okay, I'm going to go on and talk about contact reactivity model. We can see the difference in the two. Okay, so the contact reactivity model, and this is kind of what Smolden does, which is kind of what like I said, I'm going to kind of follow my understanding of how Smolden works for this, is going to be now that instead of having a rate of reaction when you're within this separation, you react instantly. Okay? So as soon as you hit the boundary here, you react. That's going to just change us to a Dirichlet boundary condition. And then when you unbind, you get placed on some reaction radius, which is some larger radius outside. Because if you placed it right back at this surface, you'd immediately rebind. That would be problematic. You could never escape away. Okay. So let's use that for our other example. I guess I have up here. Okay, so the contact reactivity model. Eraser work better. So the contact reactivity model which in this case I'm going to use what's called a pure absorption or a Stochastic model. Is only a slight change. Basically, you'll see it's the following. So now we'll have d rho dt is dA Laplacian x of rho. I said that when you unbind, you get placed on a surface with some unbinding radius. So let's let above RB was the binding radius. Probably should have written that. So we'll let RU be the unbinding radius. And of course, our assumption is that RU is bigger than RB, right? You have to bind outside of where you bind, otherwise you would just immediately rebind. So we're assuming RU is bigger than RB. Now the question you might be thinking is, how do I actually get these parameters? That's a whole other issue. We probably won't have time to talk about this, but that's one thing that if you look at some of the work, say on Smolden or some of the other algorithms, you'll see there's a lot of work that goes into figuring out how to estimate these parameters from things one might actually measure experimentally, like well-mixed rates. But that's a whole story in and of itself. Okay, so my model is I have diffusion. I'm going to have a source term from when unbinding occurs. Why don't we start to write the unbinding equation? That actually makes life a little easier if you write that first. So our unbinding equation, first, how do we get into the bound state? Well, binding occurs instantly when you hit a distance RB from the target. So that just says that rho is 0 when x minus x naught is RB. So we just have a Dirichlet boundary condition. Okay? So what does that give us in this equation? That gives us a source term of the following form. Grad rho dot eta ds of x. Where, what do I mean by that? So if this is my target and the radius is RB, which probably no one can see that because of how small that is, but if this is my target and I assume the radius is RB, then I just mean the inward normal. Inward unit normal, okay? So all this is the total diffusive flux into the reactive sphere. Okay? So that gives me the probability per unit time I bind. I just calculate the total flux into the sphere, because as soon as I hit the boundary of the sphere, I bind. Unbinding is exactly the same from the perspective of the bound state. You fall off with the rate mu, right? And then the last thing is, how, when you unbind, do you come in here? Well, we said you get placed on the sphere of radius RU bigger than RB. So that corresponds to a source term of the following form. And we'll write out what this means in a minute. So here I mean the area of the sphere of radius RB, the surface area. And then you have to have what's called a delta surface measure for placing you on that sphere. Times rho v. Okay. Now, what do I mean by a delta surface measure? Probably many of you know, but if you don't know, what I mean is the following. So this is a generalized function or distribution that has the following property. So a delta surface measure if phi is a test function, so it's just a nice function, sufficiently smooth, then we define formally that the integral over R3 of phi of x times my delta surface measure just turns into the integral over the surface. Whoops. Okay. Does that make sense to everybody? So basically, I have a source term here that just says, if this is 1 over the area of the sphere of radius RB about x naught, this just says I uniformly distribute when I unbind on that surface. So I'm equally likely to be placed anywhere on that sphere. And again, there's many other mechanisms one could think of. There's no reason you have to unbind on a particular surface. You could unbind within a region. Okay? But this is kind of the common choice that's used in Smolding. Okay, any questions about that so far? No? All right, so then I wanted to mention kind of a connection between these two models, because if you think about it, and probably some of you have already thought about this, if I take lambda bigger and bigger and bigger, right, then I'm binding faster and faster and faster. And so you might conjecture that if the rate in the volume reactivity model becomes infinite, I simply recover the contact reactivity model, right? If I have an infinite rate, as soon as I hit that region, I should bind. Okay? And one can actually prove that, but there's still some interesting open questions, so it's worth mentioning. So if you ignore unbinding, one can actually prove that the volume reactivity model converges to the contact reactivity model in the limit of large lambda.
I might be wrong about this. Should RU be appearing in that equation? The unbinding radius?
Oh, sorry, you're completely right. You unbind at the unbinding radius, not the binding radius. That's a typo. Yes. Good catch. Oh, wait, at least one person's paying attention. Good. Yeah. What I had made no sense, because you would unbind on the surface, but you'd immediately rebind, right? So the whole point is you have the unbinding radius. So you have to come off at the unbinding radius. Yep. So I guess these should also be used. So you can define it on the other one. Okay, so this is just kind of an aside, but you can prove, so if you just have association, you can prove that that rho in the volume reactivity model goes to rho in the contact reactivity model. As lambda goes to infinity. And that's actually something a former student of mine worked on. I think that was, he did a simple case in 2013, More recently, actually, he's got some nice, more general cases that he's worked out that are on archive. I don't think they've been published yet. But there's still a number of open questions. So one is, there, in the special case, he could show what the rate of convergence is. So you could show, in this special case, the rate of convergence is like 1 over radical lambda. But it's not clear if that holds in general. And perhaps more importantly, actually, would be to study if you take volume reactivity and you take lambda to infinity in the reversible model, do you get back the reversible Stochastic model? So the conjecture would be yes, but I haven't actually seen a proof of it or anyone try to study that. So that's kind of an open problem if you're interested in kind of more hard analysis problems. It's very much a hard analysis problem. This is PDE analysis to show this kind of stuff. Okay, so that's just an aside that I wanted to mention. Let's see. And I guess it's worth mentioning maybe the other case. So at least formally, yeah. So at least formally, and I'm going to write this later, so this is why I'm going to mention it. So formally, I'll think of the contact reactivity model as using a rate lambda hat of xy, which is going to be infinity. This is for two particles. If x minus y is less than or equal to rb, and 0 otherwise. So this is for an a at x, and b at y to bind. So we can kind of think of it formally as we had just a rate there, whereas the volume reactivity model, there'd be some finite parameter lambda when they're within that separation. Okay. So that kind of is a convenient tool that we'll make use of later on as we go. Okay. So let's see. So maybe it's worth mentioning the contact reactivity model with partial absorption, just for completeness. I think we've got time for that. Actually, maybe we don't have time for that. Not if I want to get to RDME. Okay, so let's skip that, and let's go back now to our general model and kind of put these reaction mechanisms in and see what the final equations we get are, so that we can talk about the Brownian dynamics simulation approach. And if anyone has questions on the contact reactivity with partial absorption I mentioned yesterday, I'm happy to talk about that later on afterwards. Okay, so don't know which board to erase. Let's leave those two up, so I guess I'll erase this one. Okay. So with these unbinding mechanisms, we can write down C goes to AB in our general model. So this is, go back to our general model. And let's look at C goes to A plus B at rate mu, okay, which is still just a first order reaction, so shouldn't be too bad to write. So that term I'm going to represent through this operator. Okay, so we're going to have an operator R, A, B, C, 2 minus for the reverse reaction that acts on F. And what are we going to get for that? If we write it out, what we'll get is the following. Let's see. So it's going to be similar to what we wrote for the other one, but a little uglier, because we have to put in the unbinding mechanism. Right. So I need one thing before we do that. Okay. So one thing before we do that. So where to put where to put our molecules on unbinding, the A and B. So I have a C split apart. Where should I put the A and B? And the mechanisms I'm going to use, there's two different ones. So let's see, what were the two that I was going to use? Okay. So in the contact reactivity versus the volume reactivity, so in the volume reactivity, over here, where did we put it? Over here, we just said, let's put, when the molecule A unbinds, we'll put it at the position of the C, right? So let's do the same thing over here. So here, when it unbinds, we'll just place it at A and B at the location of C. Okay? In the contact reactivity, what we'll do is we'll place one of them on an unbinding sphere, and then we'll place the other one by reflection so that the C is between them, okay? And then you have to be a little careful about how you do that, so I'm going to follow the kind of way that Smolden does it, where you weight things by your diffusion coefficients. So the things that diffuse faster will end up closer to where the C would be. So basically, in the contact reactivity model, we're going to assume a weighting sigma I'll call the diffusion constant of A over diffusion constant of B plus the diffusion constant of C. And we're going to basically assume that if A is at X and B is at Y, when they bind, the position of C is going to be sigma x plus 1 minus sigma y. Okay, so that's the forward reaction. And I'm actually going to use that up in this model too. So the reason I'm telling you this is going to motivate how we do the unbinding reaction. So what this basically says is if you have a faster diffusion coefficient, right, that you get weighted more heavily. Yeah?
Vice versa, actually.
Oh, did I say it backwards?
The slow one should be where it ends up.
The slow one should
They
be.
have a slow
So
molecule.
you use 1 minus sigma and...
Just reverse them.
Oh, you reverse them
Sigma
for the
on Y and
unbinding.
sigma on X.
Okay.
Slow
So
molecules where things actually happen, most likely.
the slow molecule is where it should unbind. Okay, good. Glad you're here to correct me on that then. Good. Okay, but that's how you do the binding.
Same thing by binding, so vice versa binding as well. In both cases, the slow one is where things actually happen. So if you have a stationary receptor, for example, and a moving ligand, the reaction happens at the stationary receptor because it's stationary. So that's where things actually happen. So your
Okay.
weighting is based on the slow one has higher weighting.
The slow one has higher weighting. Okay, so from your argument, you give the A molecule the diffusion constant of B in its weighting.
Correct.
So you would actually do this. Okay, well, I guess that makes sense to think about that. But let's assume that we do that. You could, of course, just pick sigma to be a half, in which case you would just use the midpoint between them. Okay, so here, I guess that's the choice that Smolden would make. You could make potentially other choices. I guess I'm going to write it like this just to keep it consistent with my notes. So let's take sigma to be that. And that way the position will be chosen like that. So then when they unbind, we'll just place C based with this weighted combination. So this is where when they bind, this is where we'll place C. When they unbind, we'll place X on a weighted sphere that comes up from this. So the strategy is going to be, and Stephen, correct me if I've got this wrong, is we're going to sample the position of X on the unbinding sphere with radius sigma times RU. Is that correct, Stephen?
Yep.
and then you place the other one using this formula by reflection. Okay? And I guess now I'm running out of room, so I need to move over here. So place the other one by reflection. Place the other by reflection. So in that case, it's going to be what? So if C is at Z, you would have Y is, I guess, Z minus sigma X over 1 minus sigma. Okay, so is that the correct sampling strategy for what you do?
Yep.
Okay, good. So I'm just going to work with this strategy for everything. And of course, this is a little technical, and there's other strategies you could pick, but I wanted to kind of be as consistent with what the simulation algorithm, with the kind of popular codes actually do. So this all seems kind of messy, but it's not actually too bad to write it out. So let's see. So what we need is a function that, given the position of the C, samples where X and Y should go. Okay? So again, A is going to be at X, B at Y, C at Z, and I'll let mu of X, Y given Z, call it mu hat, be the probability density that when a C at Z splits apart, we place A at X and B at Y. Okay. And now we can actually, given our two strategies, write down what that is. So let's see. So in the VR model, the volume reactivity model, I said we just place A and B at the location of Z. Given Z, this is just going to be a product formally of delta functions. You place X at the location of the C molecule, and then you place Y at the location of X. And if you worry about products of delta functions, you probably should, but formally, actually, it all works out okay in the equations. So, okay, so hopefully that makes sense. It just says place the two molecules at the same positions. The contact reactivity model is a little uglier, but luckily we know how to encode placing things on surfaces using these delta surface measures. So we can write that out too. If I still have an eraser.
Body body.
Oh, over there. There's one on the board. Oh, okay. That board. There's too many boards. So where should we place the C? Place that. In this case, in the contact reactivity model, we'll have that mu of x, y given z is what? So we place the x uniformly on the sphere of radius sigma ru about z. So we can write that as 1 over the surface of the ball of radius sigma ru about z times our delta surface measure for that sphere of x. So that's placing down x, and that just puts it uniformly on that sphere. And then we place y by reflection. And we said, I wrote it up there, z minus sigma x over 1 minus sigma. Okay, so that looks horrifically ugly, but it's conceptually not too bad, I hope. But now we've got this function specified, we can actually write down our unbinding operator. And so let me just write it, what we get. So we get, after all that work, that R2 ABC minus, so the unbinding operator acting on FABC is just the following. It's you sum over all places you could have had an A and B pair, and then you have rate mu. We are assuming we're working in a bounded domain omega, so we have to integrate over all places that the molecule that's split apart could have been to bring me into this state. Yeah, mu hat of qia qjb given given z f a minus 1 b minus 1 c plus 1 of qa slash qia qb slash qj b. I'm going to run out of room.
Excuse me.
Yeah.
Up to b minus 1.
Up to b minus 1. No, this should be a equals 1. That should be a. You take all your current a's and b's, right, and you sum over systems where you throw away one of the a's and b's. And then you look at basically the probability density that you could have got from that per unit, probability per unit time, per unit density that you could have got from that state to your current state. So you have to take all possible A and B pairs. Fortunately, I'm running out of room here. I don't know. Is that completely unreadable to everyone or not? It's a bit unreadable, I guess. Okay. So we'll move it down the line. So times F, you have 1 less A, 1 less B, and hopefully I've given myself enough room, of the system where you have the ith A removed and the jth B removed, and you've added in a C at an arbitrary position, dz. And let's put this bracket outside. So this says, how could I have gotten into my current state? I could be in any state where I have 1 less A, 1 less B, and 1 more C. I have rate mu that a C splits apart, right? An individual C splits apart. And then this is the probability density that when the C splits apart, it creates an A at this position and a B at that position. And then I have to sum over all my possible A's and B's. And those are all the ways that I could get into this state. So, and if it bothers you, stare at it for a little bit, since I'm running out of time, and I want to make sure I have time to talk about RDME a bit. I'm going to just assume that that's okay. We can afterwards talk about it if people have questions. So that's how you come in. How do you leave? How you leave is much easier. You just leave with rate mu c f a b c. And maybe I should write that over here. So minus mu c f a b c. That's exactly what you would expect, right? That's just your normal first order reaction. If you're having C split apart at rate mu, then the total rate that one splits apart is minus mu c. Okay, so that looks really ugly, but you can just plug in what those two functions are. For the volume reactivity model, it simplifies down. For the contact reactivity model, it simplifies down, but you're going to still end up with a surface kind of integral coming out at the end of the day. Okay, so we have one thing left, and then we actually are at the point of our simulation algorithms. So the last thing is how to write down this operator. And it's basically what I've showed you before, and I think I'll just write it formally, and then since we're not going to really use it beyond the Brownian dynamics splitting kind of idea, so just to save us a little time. So let's see, how do I want to write it? So what should I get rid of? I guess get rid of that. Okay. So I'm going to assume in all our models that when binding occurs, we place the C like we described above. So the C gets placed at sigma x plus 1 minus sigma y. Okay. There's other ways you could do it, but we're just going to use that kind of deterministic placement. And in that case, with the lambda hat defined as I wrote before, so here we're going to have lambda hat of x, y. This will be the function that gives us the probability per unit time, an A at x and a B at y react. this is going to be just lambda if x minus y is less than RB and 0 else in the VR model. And what I wrote above, infinity if x minus y is less than or equal to RB, or 0 else for the contact reactivity model. Okay. So that's just the function that gives me the probability per unit time for where an A and B are that they react. And so with that, what we get for the final operator is the following. R2 plus ABC ends up being the following. So you have to sum over all the positions a C could have been at. And you have, and I'll explain what these terms are in a minute. One minus sigma y. And then you have your F of, let's see, QA union X, QB union Y, QC slash QK CT dx dy. So that's my incoming source term. And all it just says is, how do I get to the current state? Well, I have one more A, one more B, one less C. The position of the extra A and B are X and Y, and they have to be able to react to produce the C I threw away at QKC. This is the probability per unit time they react given their positions of the A and B that I added. And then this is the probability that when they react, the C gets placed at the position QKC. Okay. So that gives me my incoming flux. This is just the particle placement probability. And then my outgoing flux is a little cleaner. I equals 1 to A of lambda hat of QIA QJB FABC. Okay. And that just says that when the probability per unit time I live this state is just a sum over all possible pairs that could react. And this gives me the probability per unit time that they could actually react. So summing that up gives me the total probability per unit time that a reaction can occur. And this is very formal the way I've written it, because I'm assuming in the contact reactivity model that it's infinite in this region and 0 outside. But with a little work, you could transform this from a rate function to a boundary condition type approach. But I think the idea is hopefully clear enough, and it's good enough for what we need for the simulations. So, okay, so that was a lot of work, about 20 minutes more than I expected. But is it okay so far? Are there any questions on that? Because what I want to talk about now in my last bit of time is actually the simulation methods, which is kind of the goal here, is to get up to that. So, okay, so you have this horrifically ugly set of equations. But now, actually getting simulation approaches from them isn't too bad. And it kind of comes out in a very natural way at this point. So we're going to group everything together and kind of write everything in a more compact notation so I don't have to keep writing A's and B's and C's. And then from that, we'll see how we get out Brownian dynamics, or at least my interpretation of Brownian dynamics. Perhaps other people will have other ones. Okay, so for every possible state A, B, C, I have a different F. So I'm going to glump them all together, right? I have a coupled set of partial integral differential equations, right? State A, B, C is coupled to state A plus 1, B plus 1, C minus 1, and the other equations it couples to other. So I'm going to get a possibly infinite system of partial integral differential equations. So to write the whole thing compactly, let's make a state vector. So I'll let the vector f of t be f0, 0, 0, f1, 0, 0, and so on. So I have a giant vector there. I can glump all these operators into effective operators. So L will be the matrix, the infinite matrix. Is that clear to everyone? and so on and so forth, right? So similar for the other operators. For R0, R1, R2 plus, and R2 minus. So basically, I just put the whole thing in kind of a formal vector notation. Great. So now we can write our equation very simply as the derivative in time of f is just L plus R0 plus R1 plus R2 plus R2 minus, acting on f. And now we've made it look really easy because we just simplified our notation down quite a bit. Okay, well, everyone formally knows how to solve that, right? The solution is just e to the thing in brackets, right? So formally, f of t should just be e to the L plus R0 plus R1 plus R2 plus R2 minus t, whatever the initial state is. Everybody agree? So in particular, I know how to calculate f of t plus delta t, right? This gives me formally a semigroup evolution operator. So I know formally that the solution at time t plus delta t is just this operator with the delta t applied to the solution at time 0, right? So formally, I know, maybe I should use a new board. Write it here. Okay. So formally, again, all of this is formally because I'm working with potentially, you know, an infinite dimensional system of equations in some abstract Hilbert space. But at least formally, then I know that f of t plus delta t should be the same operator, R1, R2 plus R2 minus delta t f of t. And now you do the simplest approximation. We approximate e to the sum of the operators by the product of e to each of the operators. Right? So we just say, okay, well, this is approximately, and let me write it in the order that I think Smolden does it. And Stephen then can tell me how I'm wrong about this. E to the R1 plus R2 minus delta t, e to the R0 delta t, e to the L delta t, f of t. And at least formally, that should be first order accurate in time. Everybody agree? Right. Formally, this is a first order splitting, so we would think that the error should be O of delta t. We could do a Strang splitting or something fancier or try to do that, but this is kind of the simplest case that we might think of. So what does this say in terms of the simulation approach? So if you haven't seen these things before, it says basically, if I know my state of the system at time t, the way I can calculate the state at time t plus delta t is do my diffusion, do my zero order reaction. So do diffusion over a time step of delta t. Whatever my system ends up in, from that, do zero order reactions over a time step of delta t. Whatever my system ends up in after that, do my first order reactions, which we have two, right? The A goes to B and the C unbinding. Do those over a time step of delta t. And whatever my system now ends up after that, do my bimolecular reaction. And that gives me my evolution update for the whole thing. Okay? So let me sketch out briefly how we would do this at the process level. And then we'll go and talk about the RDME in the last little bit that I have, which we won't do the RDME. I wanted to show you how you could get it as discretization from this, but there's no way we'll finish that in time. So I'll show you it on a simpler case to start. Okay, so and maybe we should do a new board for this. So let's see. I guess over there. My eraser. Ah. Okay. So our Brownian dynamics algorithm what we would actually simulate in the computer, right? I said this is a giant system of coupled partial integral differential equations. If you think about it, if I have, say, 100 particles of A and B and C, then even just the diffusion term, this QA would be, if I'm in 3D, this would have 300 coordinates. This would have 300 coordinates. This would have 300 coordinates. There's no way I can solve these PDEs numerically. So I simulate the stochastic process that they're corresponding to. And that's where the algorithm comes up. And the kind of flow chart is you assume you know, knowing the positions of the A and the B and the C molecules. So the first thing we do is we update the positions by diffusion. And let's see, I guess I need a notation. So let's call these positions QA of T, QB of T, and QC of T. So those are the state vectors for the positions of the A molecules, the B molecules, and the C molecules. Is that okay with everyone? So I'm glumping them all together, right? Just like my other notation that I had. So then you update them very simply. You would just say QA at T plus delta T is QA at T plus radical 2D delta T times a vector of normal random variables with mean 0 and variance 1. And that would give me, right, one exact step of Brownian motion for every single molecule. So that corresponds to every molecule diffusing over the course of one time step. And I guess here I should have dA. Now you might have to worry about domain geometry, but I'm ignoring that for now. So let's ignore domain geometry. And that would just give us our diffusion step. Now if we go back here, the next step is now we do our first order reactions, or sorry, our zero order reactions. So that's going to be step 2. So to do our zero order reactions, we just have to sample the probability of the number of molecules that got created during the time step, right? Everybody agree? And that's just going to come from a Poisson distribution, right? So we create molecules at rate alpha v. So we just sample from a Poisson distribution the number that were created during a time step. Okay, and we can do that from what Dave talked about last time, right? So you're going to have the parameter in your Poisson that you sample is just going to be alpha v delta t. Does that make sense to everyone? So that's going to give me, right, that's going to give me a sample for the number of molecules we create. And then how do we position them? In the model, we just said they get positioned randomly. So you just throw them down randomly. You place them randomly in the domain. Okay, so that's our zero order reaction. Now we've got our first order reactions. So we've got two first order reactions. A goes to B and B goes to C. And we can do a similar thing there. We just calculate for every molecule a time that it would convert or a probability that during the time step it converted. And so let's see, if we write that out, what are we going to have? So that's step 2. Oops, yeah. So step 2, step 3, we have our A goes to B and our C goes to A plus B reactions over the time step. So for every A molecule, the probability per time that it turns into a B molecule we said was beta. right? So we can sample the probability that in the time window of delta t it actually converted, right? So for each a, the probability it converted to be is going to just be 1 minus e to the minus beta delta t. Right? Everybody agree? As delta t goes to infinity, that's 1. When delta t is 0, it's 0. So you just pick a random number, and you sample from this to determine if a converts to b or not. So you just sample whether it converts, if it's successfully converted. Now you could be fancy, right, and group things together and say, you know, what are the number that convert, or you could say, what's the time that each one individually would convert, or the times that the population one would convert. But this is kind of the simplest thing one might do using that distribution. And vice versa, it's the same thing for C. So for each C, the probability that it converted to an A and B is going to be just 1 minus e to the minus mu delta t. And so again, you can sample if an unbinding event occurred for each one, and then you place them like we described above. So you sample if you unbind, if each one unbinds, and you place as described above. Okay? And that brings us to the very last step, which is the bimolecular reaction. And that's actually probably one of the easiest things to do, despite it looking so complicated in the mathematical equations we wrote down. So place as described above. So the last step is A plus B goes to C. And so what's done in the contact reactivity model is just if at this point, after you've done all of this, you end up with an A and B that are within a reaction radius, you say that they've reacted. Okay? So in the Smolden type approach or the contact reactivity approach, if an A and B are closer than RB, you react them. In the volume reactivity approach, you would say if an A and B are closer than RB, now they have rate lambda for reacting, so it's the same kind of thing. You can sample a probability for them to react using the same kind of distribution. Then they react with probability 1 minus e to the minus lambda delta t. Okay. And there's a little ambiguity there if you think about it, because imagine I have two B's that overlap with an A. Which one should you react with, right? And I guess in general, the way things are done, my understanding is you just kind of, you have some ordering, and whichever one you hit first is the one you generally execute. And I should say, these steps are not necessarily exactly simulating the exponential parts. They're providing approximations to it. So you could think about exactly simulating these e to the R2 delta t's and so on. But this is what's actually, at least my understanding, done in practice. So, okay. Any questions about that? So I know I went a little quick there at the end, but yeah.
If you have some ordering, would you kind of resample? Would you like switch around the ordering each time step or something so you don't bias it always by reacting to the same one?
That might be a good idea. I don't know. Does anyone do that? So I don't think Smolden does that. I don't know. Roddick, do you guys do that in your codes, you know, or you do? Okay. So, I mean, it makes sense that you might want to do that to try to avoid a biasing. I don't know how bad the biasing ends up being in general, though. I mean, from the discussions I had with Stephen, he said he's looked at it and hasn't really seen significant effects, I think, right?
I missed the question. What was it?
The ordering that you do the reactions in, right, it's kind of arbitrary. You said, so the question is, but you said you've looked at it, and in the examples you looked at, you didn't really see a significant biasing.
Yeah, there's no effective bias. I mean, it's random, essentially. It goes by the list of molecules in the list.
But do you randomize that list occasionally or anything?
No,
Okay, but you still haven't observed any issues or
that's
anything.
right.
So, but I think your idea of randomizing the list is not a bad way to do it. And there's other ways one could think about trying to do it, but we're out of time for that, I think. So, okay. So before, let me just see if there's anything else I want to mention on Brownian dynamics. Hopefully, at least the basic of the simulation algorithm are at a high level clear. And I should say, there's lots of stuff that I've left out because there's just not enough time. So I mean, there's algorithmic optimizations, right? One thing here is you don't want to check all pairs of A and Bs, especially if you have a lot of A and Bs. So you want to have some kind of data structure that lets you quickly know which Bs are near a given A. So you can use various types of partitioning data structures and things to sort through there. How do you handle various boundary conditions on the domain? Because if we're simulating problems in biology, but there you can kind of use standard SDE methods. If you've looked at SDEs before, this is kind of the simplest SDE, right? It's just a Brownian motion, and so you can kind of use standard tricks or techniques that one might use to handle boundary conditions in SDEs. A lot of work has gone on into calculating how you can take bigger time steps. We didn't really go through it here, but you can imagine if your time step is a lot bigger than the reaction radius, you're going to miss reaction events, right? So you have to think hard about if you want to take bigger time steps, what to do to make sure you're not missing reaction events, essentially. There has been some work on that, too. And I think that's kind of the main set of things I wanted to mention. And of course, parameter calibration, which I haven't mentioned at all, but how do you actually get these reaction radii and other parameters? And so for that, you have to go and kind of try to relate these types of models back to your well-mixed models where we assume we know the parameters, though maybe that's not even true itself. But assuming we know well-mixed parameters, typically we then try to figure out how to calibrate these parameters to match up with them. So, okay, good. So in my last little bit of time, let me try to tell you about the RDME. Unfortunately, I'm not going to get through as much as I wanted, but at least we can see a little bit about how it comes about or arises. And I guess we've seen several talks now on RDME and on continuous time random walk, so hopefully that will help or has made it a bit clearer in everyone's head what we mean by that. Okay, so the kind of simple way of doing RDME or formulating it is to just say the following. So on to RDME. And it's just a simple observation. If I have just a simple diffusion equation, and let's just say one dimension, then the standard kind of discretization of this that one might do would give me the rho I dt is d over h squared, rho I plus 1, rho I minus 1, minus 2 rho I, where here rho I of t is my approximation to rho of xi t, and xi is I h. And then with just a simple rescaling, I can convert from density to probability. So if I divide by h, or sorry, not divide, multiply by h, I get dpi dt is d over h squared, pi plus 1, pi minus 1, minus 2 pi. And that's just a simple master equation that corresponds to molecules hopping, the molecule hopping from one site to each neighbor by rates d over h squared, right? So if I'm sitting at xi, I can hop to my neighbor xi plus 1 at rate d over h squared. When I'm at my neighbor, I can hop back and so on. So we have a very simple way to approximate diffusion of molecules on a grid as just first-order reactions, right? This is just a first-order reaction. Every molecule has some exponentially distributed time to hop from a given location to a neighbor, and that's going to be d over h squared. So the kind of idea, I think, in the original RDME formulation, which at least when I first saw it was in the work of Gardner, is basically to say, let's take the well-mixed problem and put it at every spatial location. And then we'll just let molecules move between my different spatial locations with hopping rates. Okay? So it's to kind of combine the two. So that's kind of the simplest formulation of the RDME. So if we write it down for our basic chemical scheme that we had there, we just introduce diffusion as a new reaction. Diffusion as another reaction. So my system there, if I let AI be the number of molecules, let's use little ai. Yeah, no, it's fine. Get number of molecules of species A at location I. Then basically, for the reaction system that we just looked at, we would get the following set of reactions that we would simulate in an RDME. So we would have reactions that, in one dimension, AI can go to AI plus 1 at rate d over h squared. AI can go to AI minus 1 at rate d over h squared. And then all those other reactions. So you can create a molecule of species A, I, at location I. A molecule of location I of species A can convert into one of species B at rate beta. An A and a B at location I can react to produce a C at some rate K. So we use the well-mixed rate there. That's the basic idea. And then the reverse reaction, a C can make an A and a B at some rate mu. And of course, you also have the B reactions. So these should be DAs at rate dB over h squared to bi plus 1, and so on for the diffusion reactions. And that's at every spatial location, right? So basically, all we've done is we learned from Dave how we could simulate this as a well-mixed system. Basically, all we've done is now at every spatial location, we simulate that chemistry. And then we just add in these extra reactions for things hopping between the different locations. And this, I think, goes back, as far as I know, to a paper by Gardner. I think it's 1976, actually. Let's see, the year on that. In the Journal of Statistical Physics. Perhaps it was used earlier. That's the earliest that I've seen it used. But that's the basic idea. So the first thing one should ask when you see such a model is this physically plausible, or is this reasonable? Is this simulating any reasonable thing? We've kind of glued together two different things, right? Something that we know gives us back Brownian motion of molecules, something that we know represents well-mixed chemical systems. And we've just said we can glue the two together to get a spatial distributed model. Okay? So the kind of argument that Gardner gave in the original paper was to say, well, with the exception of this reaction, we're perfectly well posed. And in fact, if you took these complicated PDEs I wrote down and you knocked off this one guy, and you just did the simplest discretization you could think of. So basically, just discretize all these terms like you would discretize this at fixed lattice points. This would give you back this model. Okay? So with the exception of this bimolecular reaction, this model just ends up being a simple discretization of that model. So it's a little messy to write down, as you can imagine. But then you still have to worry, well, what about this? Because this corresponds in the original continuous model to two things having to find each other and react when they're near each other. Here we're just saying, well, if they're sitting at the same lattice site, there's some rate that they can react. So if I have an A and B at some location, I would just sample with rate k over the size of the lattice site, a time for them to be able to react. And so what you get, and the argument that I think Gardner made and many other people make, is that you need a separation of timescales to make sense, for this to make sense. That is, you need, within your single voxel of your grid, your single mesh element, the time to get well mixed by diffusion to be much faster than the time scale for the bimolecular reaction. Then we can assume that at the resolution of one grid site, things are well mixed and use that reaction mechanism. Okay? So let's look at what that actually implies if we do that. Okay, so let's imagine we're in 3D. So I've got my grid of voxels, so grid of cubes of width h. Okay, so now the only difference from 1D is instead of just hopping left to right, you could hop left, right, up, down, and forward and back. But you'd still hop with the same rate, dA over h squared. Okay, so the time scale to get well mixed, this is the well mixed time scale. Is going to be like h squared over d. Okay, that's roughly speaking how long it's going to take a molecule, right, to get well mixed throughout a voxel of my grid, right? That's the diffusive time scale to get well mixed. This has units of time. Where here I'm thinking of d as the sum of the a and b diffusion constants because we want them to be mixed relative to each other. We want to treat the reaction between them as well mixed. Okay. What's the time scale for the bimolecular reaction? Well, the time scale for that, call it tau r, is going to be like h cubed over k. If this is a bimolecular reaction rate, it has units of volume per time. So if you divide it by h cubed, you get the time scale for a reaction in a volume of size h cubed, right? So this is going to be the time scale for my well-mixed reaction in one lattice site. So this is the time scale for 1A and 1B in a lattice site to react. Okay. All right. So you just do a comparison. You want tau r to be much bigger than tau d. Diffusion should be faster. Plug things in and equate, and you get h should be much bigger than k over d. So you get this funny thing that you can't take your mesh too small. Okay? So the kind of physical argument and the justification that was used was basically, okay, so this RDME model where I have these hopping rates to move from voxel to voxel should be reasonable and an okay model to use as long as my lattice is not too small, because if it's too small, this mixing argument breaks down. But of course, you can't take h too big or you're going to approximate diffusion inaccurately, right? So you have this kind of competition. So h can't be too small, or you break down the bimolecular reaction mechanism. If h is too big, you approximate diffusion poorly. Okay. And that's kind of the formal justification for the RDME. Now, the problem in practice is when you have a real chemical system with many reactions in many species, it's much more complicated than this formal argument, and it can be very hard to assess if there is a regime where you can pick H where things work well, and whether you're in that regime. And the standard trick is just simulate my system, change the mesh size, and see if things stay kind of consistent. Okay? But of course, that's a little challenging. And so I don't have time to tell you about it, but there's lots and lots of work on how can we kind of get around this and make things work better. So one approach is to change how you do bimolecular reactions. Instead of saying use rate k over h cubed, you use some other mesh-dependent rate k of h. And those types of approaches will allow you, and Linda's worked a lot on these, will allow you to get a much broader range of of mesh sizes where things seem to work well, where the method doesn't seem to break down. However, an alternative approach, which is the one that I'm more interested in, and maybe I'll just sketch it in the last few minutes, is to start with this model and discretize it. And what hopefully I can kind of at least sketch for you is that I'm not going to do the general case, I'll just do a special case. But by discretizing appropriately, you get out something that looks like an RDME and that converges back to the particle dynamics model. And in certain asymptotic regimes, you recover the RDME. So it gives you a way to transition up to the RDME, kind of like what Christoph was talking about yesterday, but in a more crude manner. But it also gives you an underlying method that actually converges. And so let's look at that in the last few minutes that we have here. We'll see if I can actually explain it in 10 minutes. So, okay, so I'm going to take the Stochastic, I'm going to take the reversible binding model, the volume reactivity one, in just the case of two molecules and show you how we can get an RDME out exceptionally quickly. So let's take our reversible binding model and try to go to RDME. Okay, so I'm going to look at A plus B reversibly goes to C with just one molecule of A and B. And I'm going to write the model down because we've already kind of talked about what the interaction functions are. So the model is going to be the following. And I'll explain it in a minute. So that's just my normal, it says A and B diffuse. I'm going to let X be A, Y be B, and Z be C. I let AB diffuse. Just like in the volume reactivity model, they're going to react with some rate when their separation is less than RB. And then you have a source term that when the C unbinds, you place the X and the Y at the same position. Okay, so this just says that when a C unbinds at position X, that's where you place A and B. Okay. And you can derive this kind of from the model we wrote down earlier, from the general case, if you kind of go and plug things in. So this is consistent with the Brownian dynamics volume reactivity model we wrote down earlier. You also have your bound state. You're going to have dC Laplacian Z of rho B plus lambda, the integral over R6 of your probability for where you place upon binding. One minus sigma y. Then your lambda, I pulled that out front, so my indicator of x minus y. And my density, rho of x, y, t, dx, dy. Oops. Dx, dy. And then you have your the way you leave the state, which is minus mu rho b of t. Okay. So this is basically the model I wrote down earlier for two molecules reacting to produce a third that can split apart back into them. The only difference is now I'm letting all the molecules diffuse around. Okay? Otherwise, it's the same exact model. So it looks a little more complicated because everything's diffusing, but it's the same model. And if you stare at it, hopefully it'll make sense. And it just says when they bind, you place the C at this weighted separation between them, where the weights were as we described earlier, and as Stephen corrected me. When they unbind, you just place the A and the B at the same position as the C that splits apart. Okay. So how are we going to get out an RDME in 4 minutes? Well, we're going to get it out in the following way. I'm just going to give you what it ends up being. My eraser takes likes to hitch a ride. Okay. So we're going to do about the simplest discretization one can think of, which is a finite volume discretization. So basically, you don't need much notation, thankfully, which is why I picked this example. So I'm going to assume, let's assume our molecules are in R3. So assume we're in R3. That's why the integral's over R6 up there. We'll discretize it into a normal Cartesian grid. So my lattice sites are just points on Z3. H is the mesh width. Vi in R3 will just equal the cube with center IH. Hopefully that makes sense to everyone. So it's the cube with center IH and width H. So I'm just breaking things into a Cartesian grid. And I only need one other piece of notation. Vij will be Vi cross Vj. OK. So what I'm going to do now is what's called the finite volume discretization. And basically, what we're going to do is make the same assumption the RDME makes, which is we're going to assume things are well mixed in each voxel. So that, in particular, it corresponds to the assumption that rho is constant over Vij, because it lives in a two-variable phase space, and that rho b is constant over a voxel, say, Vk. So it's like we're expanding in piecewise constant basis functions. You can write this all out in finite element type approximations and make it very fancy, but that's the basic approximation. And then we're going to write down equations with that approximation for the probability that my A molecules in voxel I, my B molecules in voxel J, or my C molecules in a voxel K. Okay? That's the basic approach. So we're going to write equations with that assumption for Pij, which is going to be the probability that the A molecule is in Vi, the B molecule in Vj, and they're unbound at time t. And I'll call it, for consistent notation, Pbk, which will be the probability that my C molecule is in Vk at time t. And of course, these are mutually exclusive. You can only be in one of those two states. Okay? Is that all right with everyone? I can't write out all the details, but like I said, if you have questions, ask me afterwards. I'm happy to write it out in more detail if this is actually of interest to anyone. So let me give you what we get. So the basic idea is, how can I get these guys? Well, I take my PDEs and I just integrate them over the appropriate region. So you integrate d rho dt over Vij, and you integrate d rho b dt over Vk. And then you use the piecewise constant assumption. You use the piecewise constant approximation. And if you do that, let me just give you the punchline, and then that's basically, I think, a good place to stop. What you get out is the following. So what comes out are the following master equations. You get dpi of t is dA Laplacian h acting on the A coordinate plus dB Laplacian h acting on the B coordinate of Pij. So here, what I do is when I integrate those Laplacians over the box, I use a standard finite volume discretization of the Laplacian, and I just get my normal terms popping out. And then for the rebinding term, I get a term of this form, Pij. And then you get your unbinding term, which gives you PBI. Okay. And then your other equation, what you end up with when you do this is you get dc Laplacian hc, the discrete Laplacian acting on PBK. You get a source term of the following form, also the sink term, and then a source term of gamma ijk phi ij pij. Okay. And if you stare at that long enough, or you're really comfortable with master equations, you immediately say, ah, that's a master equation. And what we've basically created is a system where we have hopping like we wrote on the board I probably erased. Yes. So we have hopping like before at rates dA over h squared. So you have your normal kind of diffusion hopping. You've got your you've got your unbinding at rate mu. So a CI goes to an AI plus a BI at rate mu. And when it unbinds, you just place the A and B at the same location, in the same voxel. And then binding is a little trickier. But if you stare at this, what you can interpret it as is that an A at location I and a B at location J gives you at a C at location K at rate lambda phi ij gamma ij k. So now you've allowed molecules at neighboring sites to react to give you back product molecules. The C gets placed essentially where the midpoint between them would be, but it has to be calculated probabilistically. And you say, well, this is not quite the RDME because you've got nearest neighbors reacting. But the nice thing is that if you take a certain limit, in particular, if you assume that your reaction radius over your mesh goes to 0, then you can show that phi ij goes to 0 unless, very fast, unless I equals j. And I really should stop there. So what ends up happening if you coarsen this is that at the end of the day, you get back an RDME. You lose the reactions with the neighbors. All these reactions with neighbor terms drop out, and the only one that remains is when I equals j equals k. And if you want to see the details on this, you can see we have there's a paper that I wrote a few years ago in Journal of Chemical Physics. It only has the forward reaction, but the unbinding is kind of easy. And we have a new paper that we're finishing that has that in it. I'm happy to talk about it more. So the punchline, and the reason I wanted to mention this, even though I've went a few minutes over, for which I apologize, is that basically this gives you a way to get the RDME, is that if you just discretize your continuous particle dynamics with the kind of standard finite volume approach, which we didn't have time to go into details, then you get a model in which things react when they're at nearest neighbor sites. If you make the assumption that your interaction length, your reaction radius, is small compared to your mesh width, you get back the RDME in that asymptotic regime. And of course, there's a lot of details I had to skip because of that. So sorry I went a few minutes over, but I'll stop there. So. Maybe we should go to the next talk. I don't know. Are there any organizers here? Wow. None of the organizers wanted to come, huh? Okay. So who's supposed to, is there a coffee break now?
Yeah.
Oh, okay. That's even better. Great. So we can go to the coffee break. So they all just wanted to go to the coffee break, I guess. Okay. So we'll stop there. And like I said, since I went fast at the end, I'm happy to answer any questions offline about these steps that I've kind of skipped over. So. And I guess we start again in a half, yeah. Why don't we just say a half hour? I don't want to cut into your coffee break.